So welcome to this short webcast of 30 minutes, which is titled as Smart QA Musings. So perturbation of software is primarily about it creating disorder, disturbance. And why do we want to do? Simply because it's to assess order. And that's really what we are doing as probably folks in assurance. We create a disorder to assess, in some sense, the order. And that's basically what perturbation is all is. So all I'm trying to do is to look at various interesting things about perturbation and have probably an engaging discussion. Okay. So now I used a word in the earlier webinar called probe, where I said, what we really do as test is really probing. And probe is certainly something more than scenarios and cases that we normally think of. Probe is basically an ability to uncover something. But what we're doing is uncovering is actually a probing for clarity. So we're trying to look for something, understand better, and therefore a probe could be at a fine level, could be a scenario in a test case. At a highest level, it could be an idea. And there could be in-between levels, which could be certain actions that we may want to do, certain criteria that you want to check out, and potential issues to look for. So all these come under the context of probe. So what we really are doing is we are perturbing a system, that is disturbing a system, using some probes, right? And that's what we do. So perturbation is the act and probe is the means, right? And so when we take a probe and we do something with the probe, we are trying to disturb the system and assess how it responds. And is it in line with what we expect? And that's, in a very broad sense, is what we do. And we call it assurance, testing, whatever you may want to call it. Right? So let's look at some various interesting aspects of perturbation itself. Now, when you perturb something which is really an act, and how do you perturb? With some probes. So that means you poke the system with a probe, and there is a certain way of poking it. If you had planned all of that before, then you can say the perturbation is well planned. This is how I'm going to disturb the system, and I'm going to plan the activity. And therefore, it's in some sense a priori, right? The other way to look at it would be to say, hey, I haven't really planned it, but I do it in the spur of the moment. What you sometimes called random, ad hoc and stuff. So it's fundamentally unplanned. Now, I'm not saying that something is good or something is bad or something is recommended. I'm just trying to look at perturbation from, hey, maybe I can plan for it, maybe I can do for it. So why do we do it planned and why do we do it planned? What does it mean? Well, these are some things. So I guess when we do it in a well-planned fashion, what really happens is we have certain confidence in probes. That means I'm kind of planned, okay, here is a bunch of probes, this is how I'm going to irritate the system. And therefore, the initial idea of doing it from a planned perspective is to build certain confidence that I have some probes which will indeed find issues, if any, via the perturbation. Whereas, when you look at it from the perturbation at the spur of the moment, it's really about discovering holes in the probes itself and therefore expanding the probes. Holes could be areas that I didn't go into and therefore say, I never thought of that. And that's what we end up doing, right? So if you look at it from the view of perturbation in probes, it seems like, well, what does plan mean and what does spur of the moment mean? What do they really accomplish is confidence in the probes and expanding the probes. That's one way to look at from the perturbation angle. The other way to look at the perturbation could be to say, hey, it's periodic. We perturb every day at a particular time. So we kind of have a scheduled time in the way we perturb. So maybe every nightly stuff, we run some stuff. So what we're doing is we're perturbing a system at a scheduled time. Second, it could be whenever. I don't really have a scheduled time. Maybe at the beginning of a cycle or beginning of a sprint or end of a sprint or whatever, some time. So what do they really mean? What do they accomplish? Scheduled times when we perturb a system periodically, it is like saying, hey, I'm basically doing health check. I'm not really finding any issues. Whereas whenever I'm doing at a specific instance, my focus is on finding issues. And that's how we balance the entire notion of saying, I want to ensure the system's fundamental state is healthy by doing periodic perturbations, and I am looking for issues by doing specific perturbations. I mean, specific at specific times and specific perturbations, right? And that's really what one way to look at connecting the idea of perturbations to what we do. The other way to look at perturbation is it inside out or outside in? So what is outside in? Think of this picture that you see here, which is kind of putting various square and rectangular boxes to indicate, if you will, parts of the software or system. And I've tried to put the black one as saying, hey, I've added something new. I put in a new module, new feature, new something to the piece of code. And therefore, when I say outside in, what we're really saying is I, as a user, I am perturbing it from outside in. And the outside could be I, as a user, for example, which could be a human or another system. Or it could be from the environment. The environment itself does some perturbation on that entity up there. And therefore, this is disturbing it, right? So outside in is external disturbances which disturb the entity. The other way to look at this would be outside in. So what is the gray pictures talking about? It's probably a piece that is modified, updated, enhanced of an existing piece. And therefore, that causes perturbation. It affects in some form or fashion itself. It affects other entities maybe, and it can extend it to all the way into the environment if I pull the arrow into the environment and put this bounding box. So I can look at the perturbation as I am irritating from an external standpoint, or the system is in a way getting irritated by things within itself, which actually is exploding outward, right? And that's another way to look at the idea of perturbation. Now, what does perturbation do? Well, the act of perturbation is to, in some sense, to validate, test, assure effectively. So I'm saying I can irritate the system in many, many ways from many different angles, externally, internally, timed, periodic, etc. And why do I do that? Simply because I want to test it really effectively so that I shake it out as best as possible, and so that the experience of end users is hopefully brilliant. The second way to look at it is to analyze the perturbation itself. And why would I want to do that? What could that accomplish? Maybe it could accomplish the idea that if you analyze the perturbation as potential perturbation, it might help you regress effectively. So I'm trying to correlate the picture that we just saw on the previous slide, where we said there is an external set of perturbations that I am doing, be it from the user or be it by stimulated or irritated by the environment. And these, I want to do it from different angles, different points of view, and therefore ensure that I have well tested this. But when I have modifications and I don't know which would be affected, I will take the easy way out. And I'll say, look, let me try to regress in some sense everything. But we all know that everything is utopian simply because of capacity, time, resource, etc. Unless everything has been totally automated and stuff. So the problem that we all run into is test constitutes a certain smaller amount of effort, but retest constitute a significant amount of effort and time. So efficiency is of significant matter to regression. And therefore, what you're really trying to find out is before I perturb the system, can I analyze the potential perturbation that can be caused from inside in? And if I could do that, maybe I could attempt to be a little more efficient. And that I'm calling as perturbation analysis. And this is one way to think about it. So if I say perturbation analysis, let me decompose the apparently complicated set of cubes that you see on the left side. Perturbation analysis is really a key concept, or actually a technique in the hypothesis-based immersive session testing method. And what it alludes to is as simple as this. Think of it that we've got different kinds of entities that we want to test. Some of them are small like a component, and some of them are large as like an end user flow. So I put it across, as in a way, across that axis, as you can see, 4 of them. So what does L1, 2, 3, 4 simply mean? There are different classes of issues. Think of it as level 1 issue, level 2 issue, level 3 issue, or level 1 quality, level 3 quality, and so on. Think of it broadly like that. I will not get into details and confuse you totally. So the intent here is an entity which is getting modified. Maybe it is a component that I've added or updated and done some refactoring and readjustment to the code to maybe make it more efficient or efficient in terms of resource usage, for example. Then I'm really asking, I made a change in this, let's say, the building block, or it could be a feature, or it could be a requirement at large, higher level. But what I want to know is how could it affect and where should it affect? And therefore, could I now then only validate those? And that's what I'm trying to analyze. The analyze of a potential inside-out perturbation of an entity. And how can I do that? I can do that in kind of traveling across these axes. Like this one, it kind of tells me, hey, I modified. What did I modify? I modified certain structural ways by which I allocate and deallocate and use resources. And then you're really asking, the way I did that, could it possibly affect some other things of myself? Could it affect, let's say, the performance? Could it affect maybe the security? Could it affect my basic behavior? Could it affect my resilience? And therefore, the first question that you ask is, does it affect I move along the same axis, one. The second is, do I affect other similar entities? If all these entities were said to be the same different components or different building blocks, not a feature or a flow, could it be affecting somebody else? And that's another way to think about it, which is traveling along the other axis. And thirdly, is traveling across the other axis where it's saying, okay, I modified this, so I am affecting that flow. I'm affecting that requirement. And therefore, the mental model of perturbation analysis via this key concept could be of interest to optimize or optimize, in this case, be efficient by regressing intelligently, especially when there is probably lesser automation or stuff like that, right? So we talked about perturbation. I just kind of jumped along to perturbation analysis just to give you an idea how we can use. And we talked about different facets of of perturbation. Now, what we're really doing is we are looking at it from, I have needs which are satisfied by features, requirements, flows, but I also have expectations which really come from the higher order pieces, like on the flow or on the requirement per se. And the question I'm just trying to pose here, and I'm not saying there's a specific answer that I have, but the question that I'm asking is, hey, do I need to think of higher order perturbations as we go from evaluating basic needs and higher to higher expectations? So is the method, the kind of perturbations that I want to do, would it be of a significantly higher order? Should it be more elevated? And what may they be? Remember, this is just a nice set of musings, so I'm not providing necessarily, boxed answers, because I'm not I'm not kind of saying, hey, this is what is right or this is wrong. I'm just trying to highlight some interesting things and let us discover something interesting along the way. Okay, so this is one question that I have. Do perturbations need to be a higher order as we go from evaluating basic needs to higher expectations? Now let's look at certain other facets of perturbation and saying, what can I think of when I think of the word called perturbation? Could I think of, what is the intensity? Is it a simple Richter scale, for example, like an earthquake, or a scale 2? Or is it something like a Richter scale, which is 7, which will destroy the entire building? So what is the intensity? So when you talk about any disturbance, one thing that certainly comes across is at what intensity? And then you ask what frequency. I mean, is it just comes and then it repeats periodically every few minutes? Now, when we connect this idea of perturbation to an earthquake, it's kind of easier to fathom that, because you know that there is intensity, there is frequency, and so on. Another thing that we can look at the factors is it just a frequency, or is it a mix of what? A mix of different frequencies, some harmonics? And in the physical world, a particular frequency resonates with certain items and destroys it. Another frequency, harmonizes with something else and destroys it. So when you talk about a mix of frequencies, it can be quite different. So we're kind of looking at it as, are there multiple perturbations from different angles that are impinging upon the system to disturb and therefore create disorder to assess order? That's how you might want to read this picture. And finally, of course, is how long. I think there was a news item very recently about an interesting earthquake which occurred off somewhere. I think it's Greenland, I suspect, somewhere up there at the ocean. And I think it was a bunch of rumblings that was felt across the world over a very long time, traveling a long distance at a very, very low frequency. And this was, I think, a news item about a week or a little over a week ago, which is very interesting because I think people were confused as to what it is, because they didn't realize that it was actually an undersea kind of a stuff, but it occurred in somewhere in Greenland. So it's kind of interesting that it was, about duration here and travel therefore. So when you think about perturbation, I think these four things might pop in. I mean, more may pop in: intensity, frequency, mix, and harmonics, and duration, if you will. So what may happen to perturbations? What happens? So you perturb a system, what happens? I mean, the system is extremely resilient. It might say, stop, you don't come in. Now that, in the context of programming, we might call it defensive. So we say, look, the system is extremely defensive, that it doesn't let anything go and perturb. It just instantly stops it. And that's probably a great resilient system. At the lowest level, we might call it as defensive kind of programming. It might be done because of an architecture. It might be done because of a certain stuff. And that could be one thing that one can do to perturbation. Or it could be absorbed. System is brilliant, and if the perturbation comes, well, it's like going to a /dev/null in Unix. It's just quietly absorbed. You don't even know what happened. It doesn't disrupt anything. So remember here, I'm kind of not necessarily talking only from software. I'm trying to jump over to the physical world and kind of see some connections and therefore muse about them, right? So if I hit let's say a big soft piece and really hard, what would happen is it would just get absorbed. And it would just absorb the whole thing. And that's how, I guess, you get crumpled zones in cars. So that you ensure that when you have an accident, the crumpled zone absorbs it and therefore hopefully protects the driver and the other people in the car. And that's an interesting way how people respond to perturbations, right? Or it could be reflected. If it's reflected, then you get hit. If it's deflected, somebody else gets hit, right? And so what we're trying to do is to kind of relate some of these ideas and say, what does it mean to software? What do you mean by saying reflected and deflected? Does it blow up in front of me and then therefore affect what I do? If it's deflected, it means that I did something and then something else blew up in the other software, and therefore I don't know what happened, right? Or does it take the other terrible route of traveling all the way and you don't know what happened, but after a few days, something happened. And that was, I guess, the simplest example that can possibly think through is the fact of what was that major outage that we had in Microsoft recently? I forget the name, where the world suddenly stopped, planes suddenly stopped, everything suddenly stopped, banks suddenly stopped because somebody updated an interesting patch, right? That famous Microsoft, I'm forgetting the name of that company which did that. And then it unfortunately perturbed the entire system so badly because it quietly traveled into areas which people didn't know. Now, on a slightly different note, I'm sure you heard this story or the statement which says, hey, the butterfly that flaps its wings in South America causes a typhoon in Japan. And I think if you've read the book Tipping Point or any of Malcolm Gladwell's books, you probably appreciate that idea that the cause and the effect can be very distant. And therefore, you never know when you perturb something, what will be the effect. And that's really, really hard. And that becomes, as system becomes more and more complex, more and more terribly connected, that's a problem. And that's why I think sometimes what we're doing from an architectural standpoint is to decouple. We decouple it at the lowest level, we decouple it at the highest level. And therefore, when you say, I'm putting it as microservices and stuff, I think what you're trying to do is to decouple at a higher level so that you can fix the software or update the software while it is running. It's like fixing a plane while the plane is in midair, right? And that's some of these are architectural pieces. I'm saying, okay, I can just replace a service, another service, and system will continue to run. Why? Because it doesn't perturb the system, right? So what could happen to perturbations? Any of these, it could be stopped right there and say, you can't come in. Or it could be just, come in, I'll absorb you, and nothing can happen. Or it could be, if it reflects back completely at you, then it hurts you really badly. And if it's deflected, then it hurts somebody else and they didn't even know what hit them. It travels quietly and God knows. You don't know when it happens, when it's going to happen, right? And that's really how we want to look at. So this idea could help us think on probably more interesting approaches and strategies as applicable. I'm just trying to put the problem in a very different domain and look at what it means. That's really the objective of this discussion. So how do we do perturbations? I think this is something that we all easily can relate to. Maybe we can change the state of the system. And when we upset the state of the system, it causes irritations to the system, and system either malfunctions or it is resilient or whatever that we talked about. So one is by changing the state of what it is, or it can be or it can be upsetting the environment, maybe making starving resources, for example, resetting timeouts, for example, and stuff that you do from an external environmental piece affecting the system outside in. Third, I think, which is something that we appreciate easily, is injecting data. So we given data, some are good, some are bad. Sometimes good data upsets the system, sometimes bad data upsets the system. And you know that if a good data upsets the system, it's the basic stuff doesn't work, right? And therefore, this is something that we probably can relate more easily in terms of system state, external environment, injection of data, and I'm sure there's a few more that you can think through. How do we handle these perturbations? What can the system do? If a system is well done, it could probably dampen it, could tone it down so that it doesn't get affected. Or it could be a circuit breaker, which I think we use as an architectural pattern today. System has got enormous amount of load. What do? You disconnect. Suddenly, Bangalore requires enormous amount of power from the grid. If you sucked up all that, you will mess up the entire thermal station. So what do? You circuit break. So the idea of circuit breaker, which came in from electrical discipline, if you will, is used also in software, where you say suddenly when there's an enormous amount of load, you break it so that you don't upset the others. So that could be one way of handling it. The last term is the most terrible part. You resonate. So when you say resonate, I mask the frequencies in such a terrible fashion. When I resonate, it's just a runaway system, uncontrollable. You don't know what happened. And that's the analogy that you use in the non-software world for that is the nuclear reactor. If it resonates so badly that it runs away, then you have a meltdown. And that's why you put an uranium rod to ensure that you don't melt away and you can control that reaction and suck up the power. So those are the three things that we can do, and that's what we're trying to assess most of the time is system toning it down. Is it absorbing it? Is it stopping it? Is it kind of deflecting it? And that's what we're trying to assess. And that's really the quality piece, right? And that's to give, look at it from how to do and how to handle and so on. And finally, why do we do all this perturbation? Why are we constantly disturbing? Because the interesting thing is disorder and order philosophically are two ends of the same coin. And what we really trying to do is to disrupt the system to assess the order, to assess the compliance of what it is intended to do, to judge the robustness of how it would behave to extraordinarily interesting situations, to be able to scale so that it's future ready, because you never know sometimes how the future looks. Who will hack me? What kind of load? Which crazy user is going to do what with my system? No idea. So we are doing our best to future-proof it from a scale perspective, usage, situations, and so on. And finally, to build trust and confidence that we have about the product with the customers and so on and so forth, right? And that's really why we probably perturb the system anyway. Because ultimately, the interesting thing is if you had no disturbance, the system had no disturbance, then it's probably considered a dead system, right? This flat line is not necessarily interesting to human life. And that's really what why we end up perturbing system. And we perturb the system, as I told you, with a bunch of probes. At the lowest level, the probes could be deemed as test cases. Now, the last question that I'm going to ask is, okay, I maybe as a person, I perturb the system. Does it reverberate? Does it affect me? Does it change me? And that's the last question that I have before we close down in some sense. I say, how does that? So if I'm able to see an interesting response to a perturbation, maybe it is creative enough for me to create new ideas, or it gives me some judgment and then I feel better or good. So it changes the way I behave with the system, both in terms of perturbing and probe designing the probes. And that's how I constantly adjust and adjust and adjust. You may deem it as a facet of your context-driven exploratory test and so on and so forth. I call it immersive test, so to speak. So the perturbation is not something that I give and I am not affected. It is a bit of a Newton's law, but it's not as visible as we might think. So it does reverberate, and therefore it allows us to hopefully do some things better, and certainly allows us to, in some sense, be a better judge of what it is and help us make better decisions. So in a nutshell, the understanding the characteristics of certain ideas of perturbation helps us design smart probes to perturb better. It helps us discover areas that may be weak so that we can break it, you can fracture it, and so on. So if you go to material science, and when you look at the idea and use the word called fracture, and then you go and look at science of materials, you will find various properties. Tensile strength is one such property of interest that I might have, right? So you will find some interesting terms that can pop in. So let me just look. It could be brittleness, it could be elasticity, it could be compressive strength, it could be elongation strength. So all these properties of materials, in some sense, are all related to the idea of cracking, breaking, fractures, etc. So the material is brittle and stiff, it easily crack. If it is got a fantastic elasticity, then it will probably expand. So I think when we say it's cloudified, it's put in a cloud, what are we saying? As the system takes in more load, it needs more stuff, so it's elastic, it's and therefore the system grows. And in a way, that's how its system is responding to the notion of perturbation in an elastic environment by automatically sucking up more resources to do this job. Right? So thank you so much.